So we're continuing on with the note sheets from yesterday. I do want to flip back to this page here, because we talked about the set of even positive or positive even numbers. And we listed it out 1, 2, 2, 4, 6, 8, 10, and continued on. I wanted to go back to this and revisit it just for a second because there is something wrong with that there. 0 is not an even positive number. 0 is considered to be even, it is just not positive. Because 0 is an even number, it just does not have positive or negative assigned to it. It's not a positive number. So I just wanted to go back to that and just fix that for whatever reason. My brain just said 0 is good for even and positive, and we kept going. It wasn't until later in the day yesterday it finally caught back up with me. So just wanted to talk about that there. We went through the number types and their symbols. Talked about this here. We talked about subsets. And I believe we were on C. We finished C, okay. We're on D. So we talk about these subsets. A subset, every element of the subset has to be contained in the other set. So when we looked at this one here, set E, F, G, H, we're listing all the non-empty subsets. So what would one of the sets be? E. Then we could have F, then G, and then H. And I did hear EF. EF is going to be one. For me, and especially making sure we get all the subsets, as we saw yesterday when we had 2 elements in a set, we had 3 subsets, yes? When we had 3 elements in the set, we had 7 subsets, so they are getting bigger. So especially for this one here, just for my own sake and trying to make sure I don't miss one, I always start with ones first. Then we would go to EF, yes. So the next one, our 2 element sets, we could say EF. We could also say what? EG. Then we could have EH. And I think I heard FG, yes? Yeah, because FG also works. Then we could have FH. Any other subsets with 2? There's one more. We could also have what? GH. And I like going one at a time, so EF, EG, EH. So all those are covered. Then I move from E to F, FG, FH. Then we have GH. Because that helps us be able to make sure we didn't miss one of the 2s, because there's 6 of them. So there are a good number of our 2 elements. What can we do next? EF, G, we could have 3, yes? Now with 3, just to make sure, because again, we're going to have a few, I keep the first 2 elements, EF, in this case the same, and then change that third one, all the iterations that we could have, because we can have EFG, but we could also have EF what? H, yes? Because that'd be the next one. EFH. Then we could have EF. Is there any others with EF? No. So I'm going to keep E the same, but we can change F to what? G. So we can say E, G, H. Yes? E, G, H. That's no one. There's not another one after H. And we can't move G any farther down the line. So that means we've done all the 3 termed ones that start with E, yes? That means we could also have a 3 one that starts with, so we can say F, G, H. I think that's actually it, isn't it? Yeah, because we can't move H any farther down the line. We can't move G any farther down the line. That's it for the 3s. Are there any others? There's one more. E, F, G, H, because it can be a subset of itself. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We have all of them. These are all the subsets for this year. Kind of crazy how it increased this fast. Went from 3 elements having 7 to 4 having 15. That is a lot. Yes? Ends up being, let's see here, 2, 4, 8, 16, 31 if we have 5 elements. That is a lot of subsets. Incidentally, you can actually find the number of subsets by the equation 2 to the nth power minus 1, where n is the number of terms that we have. Because here 4, all that's saying is that 2 to the 4th power minus 1 is indeed 15. We would have 15 subsets. And it does get very big very quickly. So if we had 6 terms, we'd have 63 subsets. I don't think we want to try a 6-term one. That would take a lot of time and be very tedious to try to list them all out. Make sense? We feel good with subsets? Again, not a whole lot to them. It's just tedious making sure we list every single one and don't miss any. Questions on subsets? Bounded and unbounded. We're talking about intervals on number lines. We consider it to be a bounded interval if it has 2 endpoints. It is a line segment. We call them line segments in geometry. There is 2 definite endpoints. Now they could be opened or closed, but we will have a definite start and a definite end. Unbounded, one side is closed, the other side is open. It's going to continue in one direction or the other. And there's 4 main types of bounded intervals. This is all written out on your notes. Let A and B be 2 real numbers such that A is less than B. All that's saying is that we have 2 points. We have 2 spots on the number line. A is less than B. One's to the left, one's to the right. No matter what the value of A and B is, A is always going to be smaller than B. So if we picked any number for A, say -7, we know that B has to be bigger than -7. That's all that's saying. Then A and B are the endpoints of 4 different bounded intervals on the number line. We have 4 different options that we can have. Our first interval, we define it by the inequality that A is less than or equal to X is less than or equal to B. Our interval notation, we have bracket A, comma, B, bracket. Because our brackets say that those 2 endpoints are closed, they're filled in. That especially in an expression, those 2 points are included. They are true for the inequality. Our second type of bounded interval is our open circles. A is less than X is less than B. Everything between A and B is included, but A and B are not. So we have open circles for A and B. And our last 2 are very similar to each other. The top one we're saying is that A is less than or equal to X is less than B. Bless you. Whatever our value of A is included in the number line, B is not. And the one below it, A is less than X is less than or equal to B. The A value is open, it's not included. B is, so we fill it in. For intervals, we use a bracket to include, parentheses to say it's excluded. Does anybody know what number is always not included on a number line? Infinity. Infinity and negative infinity is always going to be a parenthesis, is always, especially in interval notation, it's always a parenthesis. We can never include infinity. No matter how hard we try, it does not work. Okay? That seems like an odd concept, an odd statement, but there are infinities that are actually bigger than other infinities. Infinity is not an actual, technically not an actual number. It is more of a concept than anything else. And we'll get more into that here in a minute. The other type of interval we have is unbounded. Unbounded intervals. Let A be a real number. We're just saying A is a real number, it's on the number line. As we talked about yesterday, there are such things as non-real or are complex or imaginary numbers. They actually hang out above a number line. Not on the XY plane, they're just above it. They hang out in the complex plane. We have one of these here. The first one, we say that X is greater than or equal to A. Interval notation. We have bracket A, comma, infinity, parenthesis. Bigger number is always on the right, smaller number is always on the left. The next one we have is that X is greater than A. So we have parenthesis at A because it's now not included, comma, infinity, parenthesis. The next one we have is X is less than or equal to A. So since X is less than A, it's all the points to the left of A. So we are now going towards negative infinity. So we have parentheses, negative infinity, comma, A, bracket, because A is included, we fill it in. Anytime we fill in one of the two ends, we have a bracket. Last one of the four that we have is X is less than A. So since we have less than and not less than or equal to, we have parentheses, negative infinity, comma, A, parentheses. Sometimes, especially when we're writing this out as an inequality or an interval, it sometimes is helpful to graph it out so that we can picture it, see what's going on. Do we have two endpoints? Are we going to an infinity or negative infinity? What is happening? And the interval notation helps us be able to write that in a simple, sometimes simpler fashion. And now the question is simpler. Why is the interval notation simpler than inequality? They seem about the same. And for this here, yes, I would agree that here inequality notation, interval notation is not making a big difference. But especially when we get into, we won't deal with it too much here, but especially in calculus, trig, some of the higher level maths, we do have solutions on intervals, and we have multiple intervals. And it would be saying that the solution, you don't have to write this down, is that negative 4 is less than or equal to X is less than 3, and 5 is less than X is less than 14. We can have multiple inequality statements that are showing that this is true. This is a solution for a system or a higher degree polynomial function, or this here, where we can say that the solution in interval notation then it would be where we can write this using interval notation instead of inequalities. Y'all start seeing how that's a little bit nicer. We're not having to do all the inequalities and statements. It gets bigger with inequalities. But that's here nor there. Questions on this so far? Questions about what's the last box? There is such thing as having an interval from negative infinity to infinity, all real numbers. We could have the whole number line. It is possible to have the whole number line. I did not put the inequality statement for it because it's really a compound inequality. We'd have to have two statements to make it true. But essentially it's saying that it's all real numbers. It's everything on that number line. Questions on these here? Okay. Let's look at some examples. Write each interval, each inequality in interval notation. -2 is less than or equal to x is less than or equal to 3. So we're going to be using brackets and parentheses in our endpoints here because we do have two endpoints. Now, sometimes it is helpful, and some students have found it helpful to graph it out, to look at it and see what are we looking at. Now, for some teachers, they're going to want the whole number line. We're going to want 0 and our points and try to scale it out. No, I don't want you to do, that's fine. The main thing I'm focused on, especially if you have to graph it, are the numbers in the right spot. So if we look at this here, our two numbers, our two endpoints are what? -2 and 3. So we have two specific spots, yes? -2 or 3, which one would go on the left, which one's going on the right? Yes. At -2, would it be an open circle or a closed circle? Is it included or is it not? Because less than or equal to, that equal to says it's included, so we would fill it in. The 3, if we look at the inequality, can we say that the 3 is included or not included? It's included because we have the equal sign. And then we shade everything in the middle because we're saying the values of x are between -2 and 3, so it's everything in between. Questions on how we graph that? So we have two endpoints, yes? So, excuse me, that's our bounded, our A and B. So we do have two distinct endpoints, -2, 3, because bounded we have A, B right next to each other. And we use brackets if it's included and parentheses if it's not. Now, since both of these are included, both of them would get brackets. Questions on this here? We ready to look at B? X is greater than -1. How many endpoints do we have? 1. We just have 1. Oop. And it is -1. So this is going to be one of our unbounded, because we only have one endpoint and it's going to go in one of the two directions, either left or right. Now, is the circle going to be opened or closed? Open. Doesn't have an equal sign, does it? Now we need to see, are we shading to the left or to the right? To the right. Now there's two ways to tell. One, since the X is on the left, we can shade towards the arrow. We know that the arrow points to whichever one is going to be bigger, yes? So in this case, X is going to be the bigger value. So that means we need to include values that are bigger than -1, which means we have to shade to the right of it. Make sense? Another way we can do it if you're not sure is we can pick a value. Say 4, and we can plug it in. Is 4 greater than -1? Yes, that is a true statement, so it has to be included in the shaded area. Is it included in our shaded area? Yep. So we did shade the correct direction. Now for our interval notation, we will have -1. What's our other endpoint? Infinity. Positive or negative infinity? Positive. So would it go to the left of -1 or to the right? To the right, because bigger numbers on the right, smaller numbers on the left. If you have trouble writing infinities, I don't know if you've heard this trick, take your paper, turn it sideways, and draw an 8. Now, -1 is not included since we don't have an equal sign, so we have a parenthesis. Infinity or negative infinity will always have a parenthesis. Now, these next two here are essentially the same thing we've been doing. They just didn't give us the inequality for it. C, we do have an line, and we do have two endpoints. The endpoints are what? -3 and 4. So we can say the two endpoints are indeed -3 and 4. -3. Would we have a bracket or a parenthesis? Bracket, because it is included. How about the 4? Parenthesis. Parentheses are not included. Brackets are. So since it's open, we would have a parenthesis. And that would be it. Questions on this here. Now, one of the things to keep in mind, on interval notation, we do not have an x. We do not put x's or the variable in interval notation. Inequalities, when we write an inequality, that's when we need the x. We need to say, how is it relating to a variable, a number that we could plug into it? Because if we wrote this as an inequality, we would have x. We're saying that -3 is less than or equal to x. Our values of x are going to be bigger than -3. But they can't be bigger than what? 4. So we are also saying that x is less than 4. Since it's not filled in, we just say less than. We say less than or equal to on the other side because it is filled in with the -3. We kind of see those two. Yes? Okay. Let's look at D. How many endpoints do we have? 1. And it's going to go indefinitely in one direction. So we do have an endpoint, and that endpoint is at 3. Okay? So since we are going in one of the two directions, so we will have to include infinity or negative infinity. It's going to the left, so we would need which one? Negative infinity. Since it's going to the left, the negative infinity will be on the left. The 3, parentheses or bracket. Bracket, because it is included. Negative infinity, parentheses. Questions on this here? We feel good with these here. Sweet. Let's go to the next. So, before we get to set builder notation, there is, again, above and beyond. I like bringing this thought experiment up, especially when we start talking about infinity. Because it's one thing to know, and it's another thing to know. I think y'all have heard that enough times. Yes, there's knowing and knowing, and there's a big difference between the two. You can know something logically, and you can actually understand and know it. And I think this is helpful for understanding that there are some infinities that are bigger than others. So the thought experiment is this. You work at, you're a receptionist at the Infinite Hotel. The interesting thing about the Infinite Hotel is there is an infinite number of rooms in this hotel. And on this one night, every room is booked. It is completely full. There are no open rooms. And a customer comes in asking for a room, and being the clerk and wanting to accommodate, you need to figure out a way to get him a room in this Infinite Hotel, even though all the rooms are full. So you had a thought, and what you do is you call up the person in room 1, ask them to move to room 2. Person in room 2 moves to room 3. Person in room 3 moves to room 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9. Everybody moves down 1. Infinite rooms. Room 1 is now open because there are an infinite number of numbers, but we started out with infinite number of rooms, yes? We just made it one bigger. Y'all see this here? So even though we had infinity, we just made it bigger, yes? Okay. Let's take it a step further. We have infinite hotel A, and being an entrepreneur of a hotel ship that they are, they built a second one next door. We have infinite hotel A and infinite hotel B. Tragedy struck the night before, or struck today, and hotel B burned to the ground. Luckily, everyone was safe. Everyone was able to get out. But they don't want all the people that were in hotel B to not have a room for the night. So they're going to put everybody into hotel A. But again, hotel A is full. Again, we have a genius concept. Instead of having go 1 to 2, 2 to 3, 3 to 4, everybody go down 1, let's move the person in room 1. I'll write this here because they're gone. Person in room 1 is still going to go to room 2. The person in room 2 is going to go to room 4. Person in room 3 is going to go to room 6. We're moving every person to the next even number. How many even numbers do we have? Infinity. We have an infinite number of even numbers, yes? We also have an infinite number of odd numbers, which means you can take everybody in hotel B, that infinite amount, and stick them into the first. We took infinity and increased it by an infinite amount. Are you kind of getting the picture of why we can never get to infinity? It is a thought, is this concept. This here can get even bigger. We can actually manage to fit 7 different types of infinity into one. It gets more complicated the way that you have to do it, but it is possible. And I talk about this not so much that this is going to come up again, but for us to be able to try to get an understanding of infinite is huge, bigger than we might think. And some infinites are bigger than others. Now we are going to start talking about set builder notation. There are 3 parts of it, and there's a use for this here. Okay. So set builder uses symbols to define a set of terms of the properties of the numbers of the set. So we're trying to define something in terms of a set that describe the property. So this symbols to define a set in terms of the properties of its members. There's an easier or simpler way to write it. Now I use these symbols as just a way for us to see it and help us understand it. We're not going to have brace, triangle, bar, circle, brace. The triangle, what goes in there is going to be our group. What is our group? What type of numbers are we talking about? For the most part, when we talk about real numbers, we're talking about inequalities, intervals, we're just going to put an X there. Because the way that reads with just X is the set of all real numbers X. For that there, it's our group. Are we talking about real numbers, whole numbers, integers, rational? Normally won't use irrational, but integers, natural numbers. That can change. The bar is such that. That's literally what it is. Because if we had brace X bar, all this says, and again, I said it yesterday, mathematicians have a tendency to be lazy, yes? I wrote a brace, a variable, and a line, yes? The way we read that is the set of all real numbers X such that. We put a lot of words into 3 symbols. Such that. Where the circle is, we describe this set. What type of numbers are we talking about? What type of numbers are we looking at? How are we going to define them? Because up to this point, all we've done to list a set is we just wrote the numbers out, like we looked back earlier. 2, 4, 6, 8, 10, 11, or 12, 14, 16, 18, 20, 22, 24, 26, and we put the dot, dot, dot. Because it is, we can set a pattern, it's fine, we're good there. If we did this in set builder notation, we're saying that we have the set of all real numbers X such that x is even and x is greater than 0. So for our positive even numbers, this here, so the set of all real numbers x, such that x is even and x is greater than 0. We listed all of them. We didn't have to set a pattern. We didn't have to do anything like that. Literally, this here just said we got it covered. That is all of them. So we can have words in here. We can have inequalities. We cannot have interval notation. We cannot put interval notation in set builder notation. Okay? Questions on this here so far? After chapter 1, we're not going to have to write set builder notation ever again. Y'all are not going to have to write set builder notation ever again. I, on the other hand, am going to have to write it every year. So, what we're going to do here is, especially for the first 3, we are going to look at these here and see how they look on a graph. The only one that we really are not going to be able to do on the graph, I don't know why I don't change it, is the last one, x is even, because that's just points. So if we look at the first one, x, brace x bar, x less than a. What this is saying is the set of all real numbers. So brace x bar is the set of all real numbers such that we're saying that whatever we plug in for x is a real number, any number on the number line. And we're specifying that x has to be less than a, yes? So whatever this value of x is going to be less than a, okay? Since it is less than, the circle would be open. Would we shade to the left or to the right? Left. That's all it says. Does it feel like it should be more than that? Yeah. The next one that we have is we have brace x bar, the set of all real numbers such that what? X is not equal to 3, yes? So we do have a point. We have 3, yes? Okay, I'll put a circle there. Can x be 3? No, it says x is not equal to 3, so that would be an open circle, yes? What could x be? Anything, yes? Because we said the first part, the set of all real numbers x. X can be any number such that x is not 3. It goes out both ways. Because we're saying x is any number but 3. It can be anything else. It just cannot be 3. That's kind of nice, isn't it? Let's look at the next one, the set of all real numbers x such that -4 is less than x is less than or equal to 6. So here we do have 2 intervals. We have -4 and 6. At -4 it is open. At -6 it is closed. And then we shade in the middle. Really all this asked us to do, especially with the graph, is graph the inequality -4 is less than x is less than or equal to 6. That's really all it said. Set of all real numbers x such that -4 is less than x is less than or equal to 6. Now, depending on how we want to do this next one, that E looking symbol is element. X is an element of this here. Because we could say, we could fill in a Z there. What that means is that x is an element of the integers. X is a part of the integers. It's not a part of the real numbers anymore, such that x is greater than or equal to 9. Graphically, that's not as nice to look at, especially not real numbers. Because we'd have -9 and we would include it, yes? and it'd be very tempting to shade which direction. Because it would be tempting because we're saying x is greater than or equal to -9, yes? So we'd want to shade to the right, yes? We can't shade to the right. Because what's one number immediate? Because right in front of it, we do have, say, -8, yes? That wouldn't be included. Would -8.5 be included? No, that's not an integer, is it? So can we just shade to the right? No, because really what we have is -8, -7, -6. It's just a whole bunch of dots going all the way through because we can only have those integer numbers. We don't have anything between it. Do you see why it's not as nice to shade, especially with integers, and why the last one, the set of all real numbers such that x is even? Now we're getting even more complicated because the line's not going to be everything. We're going to have those specific spots for our even numbers. So, questions on this here? So, I think we're getting the hang of this here, and especially how we're going to be graphing these, yes? Because would y'all agree that it feels like, especially with set builder notation, what we're doing, especially graphing, should be a lot more than just graphing an inequality? Because if we look at the first one, the set of all real numbers x such that 2 is less than x is less than or equal to 5. So we have two spots on this number line, yes? And they would be where? 2 and 5. 1, both, or none for a circle shaded? 1, which one? The 5. And where are we shading? When x is in the middle, we shade in the middle. Because it'd be the right of 2 and to the left of 5. Because the value of x can only be between 2 and 5. Because when we have one statement, it has to make both true. The absolute value of x such that x is less than or equal to 0 or x is greater than 4. How many endpoints or how many points do we have? Because we have one at 0, yes? And we also have one at 4. Now with or statements, hopefully by this point you've talked about or statements or sentences up to this point, because or, you can have one or the other, or technically you could have both, because you could have a sandwich, or you can have a hamburger or a hot dog, or technically you could have both. But we do have two statements, and they would both go on the number line, because as long as one of them's true, we're good, because x is less than or equal to 0. Since it's equal to, we would fill in and shade to the right, or sorry, to the left. 4, would we fill it in? No, but then we would indeed shade to the right. So it would go in either direction. Yes, sir?
It's possible for a statement to be that
there is nothing?
Like the 0 like go through the 4.
Like this here? Because if we switched it, if we switch this, and I think that's what you're asking, if we switch the symbols, well, because now x is greater than or equal to 0, yes? All the way here. Or x is less than 4. So we covered up the entire number line, yes? They are going towards each other. So we would have the entire number line. It would be all real numbers. Actually, it would be still 4. Because again, or statement, one of them must be true, yes? And with 4, because that's a good question about 4, is 4 less than 4? No, that's not true. Since it is an or statement, is 4 greater than or equal to 0? It is indeed greater than. With or statements, one of the statements has to be true, and in this case, one of them is. If it's an and statement, we would have to have both. Above and beyond this is the last thing we'll talk about before the bell. There is something considered, well, never mind. Go to lunch. We'll finish this note sheet tomorrow, and you will have a homework after that point.